In the second part of Notes D, we're going to go over some quantum mechanic basics and then apply that to how to write electron configurations and draw orbital diagrams. We're also going to include a few of the new things that IB will do with these arrangements. I would highly recommend having your own copy of the periodic table handy as we go through the notes. Before we dive in, I want to go over a little analogy that I think does a pretty good job of explaining some of the problems with what we're about to try to do. With quantum mechanics, we're trying to describe something that is so small and finite and specific and complicated that we just don't have the mechanics and the vocabulary to fully capture what's going on. So the analogy here is that if we're trying to play a really nice piece of music, but we have boxing gloves on, how is that going to come out? Are you still even going to be able to tell what's going on? It's very difficult, of course. So when we do our best to explain where these electrons are, just keep in mind that it is very specific and complicated, and we are just doing the best that we can to try to describe what's going on to the best of our knowledge. So quantum mechanics is all about probability. We're going to describe these things called orbitals, and they're going to come in different shapes and sizes. They're going to be positioned differently. They're going to have different orientations on different axes. What we're trying to describe when we describe an orbital is where an electron could possibly be found. So within these shaded regions of each orbital, there are up to 2 electrons bouncing around for each orbital. All we know is that the electrons will probably be found within those regions, and probably not in the white space regions, probably not out on the outside, only on the inside of the orbits. No matter how many lobes an orbital has, whether it's just one lobe or whether it has many lobes, no matter what, only up to 2 electrons could be in any orbital. So there's basically 3 possibilities. An orbital could be completely empty, it could have 1 electron, or it could have a pair of electrons. But up to 2 electrons are bouncing around in these shaded regions. They might be both in the same lobe, there might be one in one lobe, one in another lobe, there might be completely empty orbital, but no more than 2 electrons can be in any given shaded orbital at a time. So there are 4 orbital shapes, and you should know them from lowest energy to highest energy. S, the lowest energy shape, is a sphere. So this is a 3D sphere. P, the next highest orbital, comes as a bow tie shape or an infinity symbol looking shape. And that could be oriented on the x-axis, the y-axis, or like coming towards you and away from you in what they call the z-axis. So this is 3D orbitals. We could have 3 different orientations of the P. You don't necessarily need to know the shapes for the next one, but you should know D would come after P, and then F is the highest energy orbital. When we talk about energy, we're also talking about distance from the nucleus. So just like with ground state and excited state, S would be closer to the nucleus than P, and then F would be the furthest away from the nucleus. When we learn how to do electron configurations, we're going to use a series of quantum numbers. These numbers are going to try to describe the location of an electron. So kind of like an address would describe the location of a house, we are trying to describe the location of an electron using a set of quantum numbers. The first quantum number is called the principal quantum number, and it actually goes all the way up to 7. So we could have 7 different energy levels. The first energy level would be the closest one to the nucleus, where energy level 7 would be the furthest from the nucleus. These energy bands describe the distance from the nucleus. The principal quantum number is also the only full-size number. When I write electron configuration orbitals, the 4 in 4s1 would indicate that I am in energy level 4. The second quantum number is called the angular quantum number, and the symbol for that is actually usually written as cursive L. It's a lowercase l. And the angular quantum number is not so much a number, but actually the letters S, P, D, and F. So the angular quantum number is going to describe the shape So if I had for S1, my quantum number, my angular quantum number would be the S, indicating that I was dealing with the spherical shaped orbital. One trick that we're going to use when we write electron configurations is by using the periodic table to indicate when to use quantum numbers 1 through 7 and to use the angular quantum numbers S, P, D, and F. So there are certain blocks on the periodic table that correspond with these. So S would be your alkali metals and alkaline earth metals, the first two. Your transition metals, this entire group of transition metals, is the D block, and then the P block would be the columns to the right. Helium, however, kind of acts as if it's right next to hydrogen. It only has 2 electrons, so it only needs an s orbital. It doesn't have a p orbital. And then you have your F block with your lanthanide and actinide series down at the bottom. You should know the position of these blocks on the periodic table. The third quantum number is the magnetic quantum number, which is the letter M in lowercase with a subscript of the cursive L for the symbol. Usually people don't talk about the magnetic quantum number until you are in very, very, very advanced chemistry classes. I kind of want to go over the basics of what it's supposed to tell you, just so you have an idea of what the purpose is of the magnetic quantum number. So say I have a p orbital. There are 3 possible p orbitals. We looked at the pictures earlier. Px would go left and right on the x-axis. Py would go up and down on the y-axis. And then Pz would be the 3D version. So picture one lobe going back away from you and one coming out towards you. These are 3 different orientations I could have for my p orbital. Saying which orbital I have would be the magnetic quantum number. This is represented in a variety of ways, though. For example, I could indicate that I have a p orbital and then use a subscript to indicate what axis that is on. So p with a subscript of x, or p with a subscript of y, p with a subscript of z, to indicate each of my 3 p orbitals. What you should at least know at this point is how many different orbitals each shape could have. So if I have the S shape, the sphere, there is only one orientation for a sphere. You rotate it, it's the same. The P comes in 3 varieties, X, Y, and Z. D has 5 different shapes, and F has 7 different shapes. So these are important numbers. Anytime you have S orbital, it only happens once. Anytime you have a p orbital, it comes in 3. D orbitals always come in 5, and F orbitals always come in 7. Each of these orbitals can hold 2 electrons, so I could actually have double this number of electrons in each of these orbitals. So as a general rule of thumb, the number of shapes that an energy level can have is equal to the principal quantum number. So if I have a principal quantum number of 1, I can only have 1 sublevel, 1 shape. So that would be the 1s orbital. Now if I have the second energy level, I can now have 2 shapes. So in second energy level, I can have a 2s and I can have a 2p. The third energy level can have 3 shapes. So that would be 3s, 3p, and 3d. And then in the fourth energy level, I could have all 4 shapes. 4s, 4p, 4d, and 4f. Notice that I start with the lowest energy level, always starting with S. Then if I can have a second shape, it would be P, because that is the next highest energy. Then comes D, and then finally, only if I can have 4 shapes can I have an F orbital, because that is the highest energy shape. The next thing that I want to determine is how many orbitals that actually translates to, which is why I wanted us to have a little bit of a background in the magnetic quantum number. So in my first sublevel of 1s, S always comes as 1, so I'm only going to have one orbital. When I move on to the second energy level, 2s, the 2 just indicates that it is 2 energy levels away from the nucleus. It does not mean that there are 2 s orbitals. S always has one orbital. P is going to come as a set of 3. Always 3 p orbitals. So actually I now have a total of 4 orbitals in the second energy level. With the third energy level, 3s does not mean 3s orbitals. It means an S-shaped orbital that is even further from the nucleus. There's still just one of them. 3p, because it's a p, it again comes in 3s. And then D is always going to come as a set of 5. So this is now a total of 9 orbitals. When we move on to the fourth energy level, again, the 4 just means that it is that much further away from the nucleus. But S, there is always 1 of. P, there is always 3 of. D, there is always 5 of. And F now, we have 7 of. So that will be a total of 16 orbitals. So you've really got to be careful not to confuse the principal quantum number with the number of orbitals. That number of orbitals always comes from the magnetic quantum number. Anytime you have an S shape, 1s, 2s, 3s, or 4s, there is always just one of those orbitals. Anytime you have the P shape, 2p, 3p, or 4p, you always have 3 of those orbitals. Anytime you have the D shape, this 3d or 4d, you always have 5 of those orbitals. And if you have the F shape, you always have 7 of those orbitals. It does not matter what number is in front of the shape. The number only gives you the distance from the nucleus. One of the most important things that the angular quantum number gives us is how many electrons could be found within that level. If I always have one orbital in the S shape, then the S could only ever hold a maximum of 2 electrons. If I always have 3 orbitals in the P shape, then P could only ever hold 6, because I can only hold 2 electrons per orbital. So if I have 3 orbitals, I can have 6 electrons. Since D has 5 orbitals, I can have twice as many electrons, up to 10 electrons in the D shape. And then in the F shape, since I have 7 orbitals, I can have up to 14 total electrons. These shapes cannot hold more than this maximum number of electrons. So we're going to apply that when we write electron configurations. We can't have greater than this number of electrons in this shape. So if I'm writing 4s, the most electrons I could put in 4s would be 2. And so that would be what I could write as an exponent. If I were writing for 4p, I could have up to 6. For 4d, I could have up to 10. And for 4f, I could have up to 14. Now I can have less electrons in there. The sublevel may not be full, but I could never have more because there just aren't any other orbitals to put the electrons in. The fourth and last quantum number is called the spin quantum number, which is a lowercase m with a subscript of an s. We usually refer to the spin quantum number actually as arrows. For example, when you're doing the orbital diagram, you might draw an up arrow and a down arrow to show that those 2 electrons are going opposite directions. So there's kind of an arbitrary number assigned to this, a +½ and a -½. But really in practice, I think we use arrows to show this opposite spin. So the 2 electrons that are in the same 4s orbital, these 2 electrons, one is going clockwise and one is going counterclockwise. So we're going to show that with 2 oppositely faced arrows. And that completes the 4 quantum numbers that we are going to use to write electron configurations. Next, we're going to go over 3 important rules that guide how electrons fill an atom. So the first rule that we're going to apply to our configurations is called Pauli's exclusion principle. Exclusion means to leave out. So basically the rule says if I have a set of 4 quantum numbers that already exist, that set of quantum numbers is excluded from the realm of possibilities for any other electron. So basically, to paraphrase this, it says all electrons are special, special like a snowflake. You cannot have any 2 electrons that have the exact same configuration. So even if there are 2 electrons that happen to have the same principal quantum number, maybe in the 4th energy level, maybe they're in the shape, that S shape, same shape. They're even in the exact same S shape, or maybe in the exact same P shape. We have 2 electrons in every orbital. Okay, fine, they have 3 of the same quantum numbers, but then they would have to have a different spin quantum number. They'd be having to go opposite directions. So this really comes into play when we do orbital diagrams with the arrows, that you have to have the arrows going in opposite directions if they are in the same exact orbital. The next rule is called Hund's rule. So this really focuses on the repulsion of electrons, but there is a catch. Before the repulsion drives what the electron does, it must be of equal energy. So say I have a 2p orbital. That would automatically come as a set of 3. If I had 2 electrons, one would go to 2px, and the second one would separate in another orbital, go into 2py. And then if I had a third one, I would put it in 2pz. I wouldn't come back and pair unless I had 4 electrons. And when I did pair, I would go the opposite direction. So a couple nuances here. If you do have them spaced out, they would go the same direction. This is called being paramagnetic. There's a magnetism of them going in the same direction that is more stable than them going in opposite directions. So if they are what they call singly occupied, which would be this version, where they're 1 electron per orbital, then they're going to go the same direction. But if they're doubly occupied, like here, where we have 2 electrons in the same orbital, one would go clockwise, the other would go counterclockwise. They'd be going in opposite directions. So Hund's rule talks about the magnetism a little bit, but most importantly, it talks about the repulsion. You would never pair before you would spread out. The only catch being it would have to be in the exact same orbital because they have to be equal energy. So how do I remember Hund's rule? I say electrons are selfish. They want their own space because of this repulsion. Let's say you're going to get on a bus. This is the aisle, and you have rows of seats. Seats that are parallel to each other would represent equal energy. It wouldn't take you any more energy to pick the right side or the left side. But on the right side, there's a smelly hobo. Do you really want to sit with the smelly hobo? No. You would want to sit on your own space. You would pick the unoccupied orbital. Electrons are going to do the same thing. They don't want to sit next to something they're repelled from. They would rather go over into their own space. And we saved the best for last. The most important principle is actually Aufbau's principle. To summarize Aufbau's principle, I always say electrons are lazy. They always want to go the path of least resistance. They want to go to the lowest energy level first. Until the 1s orbital is full, you will not get electrons in the 2s orbital. 2s will fill before 2p. So notice the energy levels here. Your first energy level fills before your second. Your second energy level fills before you start on your third. But as you start to get further from the nucleus, you actually have a little bit of a problem. If you look closely, the 4s orbital is actually a lower energy than the 3d orbital. So you're going to actually fill 4s before you fill 3d. So the orbitals overlap as you get further from the nucleus. So there's a very specific order. Luckily, we can use the periodic table to kind of guide us through these overlapping sections. So first I'm going to describe the pieces of the periodic table and how they have certain patterns on them. Then I'm going to go over how to use these patterns and read from the periodic table to get an electron configuration. Notice that the helium is still considered 1s. Some people even write it over to the left side when they do electron configurations. So first let's look at the blocks. We had our shapes we talked about earlier. So the S block is your alkali and alkaline earth metals in the first two rows. The transition metals is your D block. The columns to the right of the periodic table is your P block. And at the bottom, your lanthanide and actinide series would be your F block. S, P, D, and F, sections of the periodic table. Next, let's look at the connection between the row on the periodic table and the principal quantum number. So generally speaking, the first row would match up with the first energy level. So hydrogen and helium only have one energy level, the 1s. If you look at the second row, that would match up with the second energy level, and so on and so forth until you get all the way down to the seventh row, corresponding to the seventh principal quantum number, or being the furthest distance from the nucleus. And that's going to be true for your S block and also your P block. If you look over at your P block, I start on the second energy level at 2p and go all the way down to the seventh energy level, 7p. So elements in the seventh row in the P block would be in the seventh energy level. Unfortunately, that pattern does not hold true for your D or your F blocks. So let's think about why. We had said that if I have one energy level, principal energy level of 1, I can only have one shape. So for energy level of 1, I can only have 1s. If I am in the principal energy level 2, if n equals 2, I can have two shapes. So that would be 2s and 2p. Now if I'm in the third energy level, I should have three shapes. So I can have 3s and 3p, but I'm also going to have 3d. Now the problem is the 3d row is in the fourth energy level. So for your D, you're always going to need to subtract 1 from the row because your D block will start at 3. So as you go across your fifth energy level, you have 5s, but then 4d, then back to 5p. So D is off by 1. Now let's think about the F block. If my first energy level has one shape, my second energy level has two shapes, my third energy level has three shapes, then my fourth energy level should have four shapes. So when I bring in the fourth shape of F, I should start that at 4. So I'm going to have 4F and 5F for my lanthanide and actinide series. The other thing I want to talk about with the F block is where it actually fits into the periodic table. So it's kind of a cutout, kind of like how when you see Alaska and Hawaii on a map, how it's just cut out to the side and the actual distance isn't represented. Well, in order to fit the periodic table on a piece of paper or onto a screen, for example, it's been cut out. So your lanthanide series actually belongs in between 6s and 5d. Your actinide series is going to belong on the bottom row in between 7s and 7d. So when we learn how to read this, we're going to read across. We would go from 6s to 4f first, then to 5d, then to 6p. And for the last row, we would go from 7s to 5f to 6d, and finally 7p. The last pattern that I want to point out before we go over how to actually write electron configurations is the number of blocks in each of the shape sections. So we have 4s that could hold a maximum of 2 electrons. Well, if you look at the S block, it is exactly 2 elements wide. If you look at the D block, if you counted across the D block, you would count exactly 10 blocks because that is the maximum number D can hold. Across the P block, you can count 6 boxes exactly to represent the 6 electrons that a p orbital can hold. And then our F block down here would be exactly 14 across. There are 14 electrons in our 7f orbitals. There could be 10 electrons in our 5d orbitals. There could be 6 electrons in our 3p orbitals, and we can have 2 electrons in our 1s orbital. So this number of boxes that you count across are going to translate to these superscripts representing the number of electrons. So now that we see all of these patterns on the periodic table, we can use them and read from left to right, top to bottom to get the proper order of filling. And the number of boxes will give us the number of electrons in each orbit. So starting at the very top, the very first orbit that I come across is 1s. So for hydrogen, only one box across, the electron configuration would be 1s1. But if I went to helium, the second box, then my electron configuration would be 1s2. No matter what, I always start at the beginning. So say I wanted to write the electron configuration for lithium, I would still start with 1s and go across 2 boxes. So I would write 1s2. Then the next one, starting at the left, next column down, I would go to 2s. And if I were writing it for the first element, I would write 1s1. And for the second element, we would use 2s2. If I wanted to continue that over and do maybe aluminum, I would still go through 1s2, 2s2, and now I would introduce 2p. For the first element, I would do 2p1, 2p2, 2p3, all the way up to the end where I would write 2p6. Let's go a bit further down. Let's go down to potassium. Starting at the beginning, I'm going to use 1s and I count going through 2 boxes. Then I would go to my next row down and use 2s, and again I go through 2 boxes. Then I would go across to 2p and I would go through all 6 boxes. Next row starts at 3s and I'm going through both of the boxes. Then I go across. Next is 3p, going through all 6 boxes. And then I'm going to start with my next row with the 4s. And be careful at the end. If I'm aiming for potassium, that's only the first box. So the electron configuration for potassium would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. If I wanted to go to the next element, I can change this to 4s2. Once you get past atomic number 20 and get into this D block, you have to be really careful because you are down 1 from the principal quantum number. So as you go from 4s, you're going to go into 3d, then back to 4p. If you're going from 5s, you would go to 4d and then to 5p. In your last 2 rows, you have to be really careful because you go from 6s down to, remember the F block is inserted here. So we would go from 6s to 4f, back to 5d, then 6p, onto 7s, down to 5f, up to 6d, and then 7p. So let's go from where we were looking at potassium and calcium before, let's go down a few more. Let's do cesium. So we had already gone through 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 to go all the way to the D block. After 4s would be 3d. And D has 5 orbitals. It can have a maximum of 10 electrons, and if you count, you would go through all 10 blocks. So it's 3d10. When you go to the P block, you're back to the 4th energy level. S and P do line up with the numbers, the row numbers. So this would be 4p, and you're going through all 6 blocks, so 4p6. Then you're going to go to 5s, going into the next energy level, which you're going across both blocks. But then when you go into the D orbital, make sure you go from 5 down to 4, 4d, going across all 10 blocks. Then back to 5 for the P block, So that would be 5p. You're going through all 6 blocks, and then you would get to your 6s. And be careful at the end, since we're only going to the first row, first block is just 6s1. So now that we know the trick to using the periodic table to give us the correct electron configuration, I do want to tie this back to what it is that we're even writing anyway. Why are we doing this? So let's look at a simple electron configuration. For example, lithium, which has exactly 3 electrons. The correct electron configuration for lithium is 1s2, 2s1. What this means is that in my first energy level, I have 2 electrons in an S-shaped orbital. Then in my second energy level, I have 1 electron also in an S-shaped orbital. I'm giving the exact locations for each electron that exists inside of a lithium atom. If I want more information about what those electrons are doing or how they are arranged within the orbitals, I actually need an orbital diagram. This is going to give me information about whether the electrons are paired, and it's also going to show whether they're going clockwise or counterclockwise compared to each other. An orbital diagram uses a box to represent an orbital. So for every s orbital, I will have exactly 1 box because s always has 1 orbital. Whereas for p orbitals, that will always come as a set of 3 boxes. If I had a d orbital, it would come as a set of 5 boxes, and an f orbital would come as a set of 7 boxes, regardless of the principal quantum number. It is always the number of orbitals that is the number of boxes. Inside of the boxes, we're going to use arrows to represent an electron. Every single arrow represents exactly 1 electron. So if we looked at lithium's electron configuration, 1s2, 2s1, you can see in the 1s box, we're going to use 2 arrows, whereas in the 2s box, we're only using 1 arrow, since the electron configuration is 2s1. When we do the 2 electrons in the 1s orbital, it's very important to make sure that they're going opposite directions, because we don't want to violate Pauli's exclusion principle or Hund's rule. You also want to make sure when you're filling the p, d, or f orbitals that you spread them out whenever possible. Remember, Hund's rule says that electrons want their own space within an equal energy. They don't want to occupy the exact same orbital unless they have to. So let's walk through a few examples. Starting with hydrogen, the electron configuration for hydrogen is 1s1. So I'm going to draw 1 box to represent the 1s orbital, and I'm going to put exactly 1 electron in it. So I'm going to draw exactly 1 arrow. Helium, on the other hand, has 1s2 for its electron configuration. So again, I'm going to draw 1 box for my 1s orbital, but this time I'm going to put in 2 arrows, 1 going up and 1 going down. Carbon's electron configuration is a little bit longer. 1s2, 2s2, and 2p2. So for my s orbitals, both of them have only 1 box, 1s and 2s. Remember, the 2 only tells me that it's further from the nucleus. It does not mean that it comes as 2 orbitals. When I write 2p, p always comes as a set of 3. So I have a set of 3 boxes for p. When I place my arrows, I'm going to fill them section at a time. So first, doing 1s, I would put in 2 arrows, and since it's a set, they're going to go in opposite directions. I'm going to do the same thing for 2s, a set of oppositely faced arrows. When I put in the 2 electrons for p, I want to follow Hund's rule. I'm going to spread them out. When they're in separate orbitals, they also go the same direction. That magnetism, paramagnetism. So this would be the correct orbital diagram for carbon. Say I wanted to go a little bit further from carbon to nitrogen. I would have 1 more electron. I would put it over in the 3rd box. And then if I had even 1 more than that, the 4th electron would come back. A 5th electron. See how we're pairing down all the way up to our noble gas configuration. So you spread them out and then come back and fill in going the opposite directions. If I had another electron, I would need to introduce my 3s orbital. Oh no. So let's go over a few examples of how I got those electron configurations. So we'll start with helium, which is the second element on the periodic table. So it kind of belongs in the S block like we talked about. It would only have one principal quantum number because it only has 2 electrons total, which will fit perfectly in that 1s orbital. So helium's electron configuration is simply 1s2. Boron is the first element in the P block. So first we're going to go through 1s2, and then we're going to go to the second energy level, which would first have 2s going through both boxes. And then when we get to 2p, boron is just the first box. So the electron configuration is 1s2, 2s2, 2p1. Neon, on the other hand, is the end of this first P row. So we're going through 1s2, just like we always do. Then second row, 2s2. And then when we do the 2p, we're going all the way through all 6 boxes. So the configuration would be 2p6. Next we have aluminum, which is actually the second element down in the P block. So it's on the third row, first column of the P block, right there. So we're going to start at the beginning again. We have our 1s2. Then we're going to go to the second row, and we'll have 2s2 going through both blocks. And then go over to 2p, and we go through all 6, so 2p6. Next, we'll go to the third energy level and go through 3s2. And then over to the P block, we've got 3p. But for aluminum, it is just the first element, so it's 3p1. Now for a real challenge. Uranium is the 4th element in the actinide series, so way down at the bottom of the periodic table in our F block. We're going to start at the beginning. We're going to go through the complete electron configuration. So starting with 1s2. Second row, we're going to go through 2s2. And then over to 2p6. Third row, we'll go through 3s2 and 3p6. With our fourth row, we want to be really careful. We start with 4s2, but then when we get to the D block, remember D is 1 off, so it's 3d10. And then back to the P block, we'll be back to 4, so 4p6. For our fifth row, we'll have 5s2, but for D, we're going to go down 1 to 4d10, and then back to 5p6. The next row is very tricky. So as we start off the 6th energy level, we have 6s2. From there, we actually go down to our 4f. So we have 4f, and f is always 14 max. So if you count across the blocks that are actually in the F block, it would be 14 elements. Then you're going to come back to the D block. Now we're in the 6th energy level, and D is 1 off, so that would be 5d10. And then into the P block, back up to 6. The S and the P match the energy level, match the row, so it's 6p6. As we start our 7th energy level, we want to still be careful. 7s2 is then going to take us down to our actinide series of 5f. And here we're at the end, so we want to be extra careful. We're only going to uranium, which is only 4 blocks in. So we're going to end with 5f4. Before we move on, I want to take a second to address one of the most common questions that I get in IB when we start looking at electron configurations. According to Aufbau's principle, you would fill 4s before 3d. So the electron configuration, according to everything that we just went over, would have 4s2, 3d3 written in that order for an element like vanadium. However, in the IB keys, you're going to see it written with the 4s at the end. Why do they do that? The technical answer is that some orbitals have different energies depending on whether they are empty or whether they are full. So the main thing that they talk about in the IB book is that the third sublevel will fall below the fourth sublevel. 3D would fall below 4s if the atomic number is greater than 20. Notice where that is on the periodic table. That's right before you get into the transition metals. So basically, if you do have a d orbital, electrons in the d orbital, it is going to adjust the energy level. This, however, does not change the order of filling. You are still going to fill the energy levels according to Aufbau's principle. However, once they're full, technically the energy levels are rearranged. So once I have electrons in the d orbital, I should write that with the s orbital afterwards. But I have good news. IB doesn't care as much as you would think they do. I know they have a lot of things that they are very particular and weird about. This is not one of them. They will not count off for not rearranging. They are technically accurate. I do want you to know that in case you go really far into chemistry, that it is not wrong what they are doing. It's just not a big deal right now. So you may have noticed that electron configurations are fairly repetitive. You're always going in the same order. You just have to know when to stop. So there is a shortcut, the abbreviated version of these electron configurations, sometimes called the noble gas configuration. What we're going to do is we're going to take the noble gas, and then if there's more elements after that noble gas, then we can write just those pieces. So basically we want to find whatever element's previous noble gas, write that down, and then continue the configuration. Sometimes an element is a noble gas, like helium, in which case I can just write the configuration helium and leave it at that. So I'm going to write the He. Whenever we write the noble gas, though, we do put it in squared off brackets for proper formatting, and I can leave it just like that. If I look at boron, boron's previous noble gas is also helium. So when I write helium, that's going to represent my 1s2 orbital. I still need to write the rest of the electrons, so 2s2 and 2p1. For aluminum, that was the next one down in the third row. So the previous noble gas for aluminum is neon. So if I write neon, that would take the place of 1s2, 2s2, and 2p6. That is all represented when I write neon, since that is the configuration for neon. Then I'm going to continue with the rest of it, 3s2 and 3p1. So final answer, neon, 3s2, 3p1. Next, let's look at cobalt. So cobalt is kind of in the middle of the first row of the transition metals at 3d7. So if we want to look at its previous noble gas, we would have to come back to the third energy level, this 3p6. And at that point, we can use the noble gas instead. So that would be argon. And if I put argon in brackets, it can replace all the things that make up argon's configuration. But then we're going to still need all of the 4s2 and the 3d7. Uranium's electron configuration was huge. It was way down here at the bottom of the periodic table. So that row in row 7 is preceded by the noble gas at the end of the 6th row, which is Rn, radon. So then we're going to have to start at the beginning of the 7th row with 7s2, which then goes down to 5f, and uranium was only 4 boxes in. So it would be radon, 7s2, 5f4. There is one uncommon shorthand that IB uses occasionally. They only throw it in the multiple choice every now and then, but you should still kind of know what they're getting at when they give you this. What this notation is it gives the number of electrons per energy level. So the first 2 would represent the 2 electrons that are in the 1s orbital. Then if I looked at the second energy level, it would have 2s2 and 2p6, a total of 8 electrons. So I can show that 8 electrons fulfill the second energy level. Then in the third energy level, for this example, it's just 3s2, 3p1, which would total only 3 electrons. So now I know I have 3 electrons in my third energy level. So the only element that has 2 electrons in the first energy level, 8 electrons in the second energy level, and 3 electrons in the third energy level would be aluminum. This would be the electron configuration for aluminum, and this would be a shorthand way to represent it. The good news is I've never seen them do this for any of your larger atomic numbers. Really over atomic number 20 is typically the cutoff. So here's a table from the book. You can see your alkali and alkaline earth metals. Then you would have the transition metals between there. And then this would be your 6 rows in your P block. So this is showing that there would be only 1 electron in the first energy level for hydrogen, or 2 in the first energy level for helium. So notice how the first number is 2 for all of these, because 1s only has 2 electrons, and so that's the first energy level for all of the atoms. Then as you go from left to right across the second energy level, you're adding 1 more electron, where lithium only has 1 electron in the second energy level, neon has all 8. Then as you move forward, all of the atoms have 8 electrons in the second energy level because they all have 2s2, 2p6 full. Now as you go across the third energy level, you see sodium having 1 electron in its third energy level. You see aluminum here, the example we did before, having 3 electrons in its third energy level, all the way up to argon having all 8 electrons in its third energy level. Then when you look at the couple that we have here in our fourth energy level, you see their third energy level is full with 8 electrons because their 3s and 3p are full. And now we only have 2 atoms to worry about in the fourth energy level because it does stop at atomic number 20. You have 1 electron in their fourth energy level for potassium and 2 for calcium. There are 2 big exceptions that you should know which do not properly follow Aufbau's principle. The first is copper. So this is the electron configuration as we would normally fill it from Aufbau's principle. It is the abbreviated one, so we go back to argon, and then we have 4s2, 3d9. So if we have 9 electrons in our d orbital, the orbital diagram for that particular 3D section would look something like this, where I do have 1 lone electron. That's not stable, and transition metals would much prefer to have 10 and complete their d orbital. Well, where could it get another electron from? It's going to steal it from the 4s orbital. And that's actually even better for bonding, since 4 is the highest principal quantum number. This is my valence shell. That is the electron that would be lost during ionization, leaving behind a more stable d orbital. So the final configuration, the proper configuration for copper, would start with argon, but we would actually have 4s1, 3d10. And if it were the copper ion, it would just have argon 3d10. Now let's look at chromium, the second exception. So a proper configuration for chromium would end in 3d4 if we followed Aufbau's rules. And then the orbital diagram of that d orbital would have 4 paramagnetic electrons, 4 electrons facing the same direction. Well, something that's more stable should actually have all 5 orbits in the d orbital perfectly paramagnetic. So a more stable atom would end in 3d5. Well, where could it get that one extra electron from? The 4s orbital. So again, we'll go down to 4s1 in order to have a better d orbital. That again is also going to be better for bonding because that 4s electron is the valence shell. So the actual electron configuration for chromium would start with argon, but now we'd actually just have 4s1 and then 3d5. These two atoms are the ones that will be on your IB test, but just so you know, anything ending with D4 or D9 will steal one of the s electrons. So this is going to happen for actually a set of 8 atoms on the periodic table. The last thing that I want to look at with electron configurations is how it changes if you're dealing with an ion. So what I have here are the electron configuration for the individual atoms, and I want to look at how it changes when there's a charge on the atom. So the first one is for nitrogen, but if it had a 3- charge. So a negative charge would come from having additional electrons, since electrons are negative. So if I ended with 2p3 and I added 3 more electrons, I would actually fill up that p orbital to be 2p6. We could even write that as the electron configuration for neon, since it is a noble gas configuration. Next, if we look at selenium, the regular configuration would end with 4p4. A 2- charge would mean having 2 additional electrons, again maxing out the p orbital at 6. And since that is the same as a noble gas, we can just write the noble gas configuration for krypton, Kr in brackets. Our next one has a positive charge. So a cation, a positively charged ion, can only be formed by losing electrons. So if I have 2+, I've lost 2 electrons. So those 2 electrons are going to come from this 4s shell. So if I get rid of that, all I have left is the neon electron configuration. It's important to note that I didn't actually turn magnesium into neon. What I'm saying here is the magnesium 2+ ion has the same electron configuration as the neon atom. And actually the nitrogen ion would also have the same electron configuration as neon. So it is possible for multiple atoms to have the same arrangement of electrons. And there is a vocabulary word for that. That's called being isoelectric. Next, we're going to look at a couple different types of ions. Whereas our previous set of ions all tended to be like the noble gases, this set of ions is not necessarily going to give us the perfect noble gas configuration. It is, however, going to give us something that is more stable than it would be alone. So our first atom is an aluminum atom, whose normal configuration would end with 3p1. However, it has a 6+ charge. So positive charge again means that we're going to be losing electrons to leave this unbalanced positive charge. So we're going to need to lose a total of 6 electrons. My first electron to be removed would come from the 3p orbital. Now I have 5 more to get rid of. So next, the 2 from the 3s2 would leave. So I have lost 3, I still need to lose 3 more. Now my next orbital is 2p6. I'm going to lose only 3 from that p6 configuration, leaving 2p3. This is pseudo-stable because the p orbital is exactly halfway full. Remember, we called that paramagnetic. The next ion I want to look at is chromium. Now remember, regular chromium was an exception to Aufbau's principle. So the correct electron configuration for regular chromium is 4s1 3d5. We want a perfectly paramagnetic d orbital, leaving only 1 valence electron. So when I lose, again positive, I'm losing 3 electrons. The first electron gone will come from the 4s orbital. Now I still need to get rid of 2 more, so my d5 will become d3. So this would just be argon 3d3. And our last one is a copper ion, again, an exception to the Aufbau's principle. So we have 4s1 3d10 for the proper configuration for regular copper. If I'm going to lose one electron, it's going to come from the outermost shell. So the 4s valence electron will be the one that goes. It's only losing one because it's only a +1 charge. So that leaves argon 3d10, which is actually surprisingly stable.